Hello everyone, welcome to my channel, and I do educational videos on this channel. Today is our 429th video on the reciprocal system of theory from Dewey B. Larson. And this is a system of theory, meaning basically it's a theory of everything. If you learn how to manipulate the theory and learn how to apply it, you can apply it to any subject that you'd like. It can help round out your holistic worldview and give you the ability to make paradigm shifts, to awaken yourself to 5D consciousness, and all kinds of other stuff. But you've probably never heard of it before. I've actually never, ever, in 20 plus years of studying the reciprocal system, I've never met another person in person who's ever heard of them before. But I think I won't be saying that if I live to be an old man, he will be a household name, and everybody will be studying his theory because it will be the underlying, theory for every subject, not just physics and chemistry and astronomy, not just philosophy and psychology and economics, but also religion and really any other subject that you want to apply it to. Now, Larson's history is that he was an engineer, and he stumbled across some epiphanies early in his life, in about the 1930s, and developed them over the years. Realized that he had some major answers on his hands, or potential answers. And in 1959, he put out his two fundamental postulates. Just 2 sentences, 45 words, about how the universe operated. He took those words, and then through a process of deduction, an if this then that approach, he derived his theoretical universe, a universe about how the universe would look if his fundamental postulates were correct. And then in his books, he took his theoretical universe and he compared them. He compared his theoretical universe with the universe that was measured by the scientists, the legacy scientists, in their laboratories and observatories, and compiled in their scientific tables. So, for example, today we're going to be looking at his book called Basic Properties of Matter. This is a book on chemistry, and we're in chapter 4, which is on compressibility. So Larson's his deduction, through his process of deduction, he was able to deduce equations for the various properties of matter, including equations for compressibility, depending on what kind of an element or compound we're talking about, and also like what kind of conditions, temperature conditions, and so on. And then in this book, he compares his theoretical findings with the findings that cost the scientists trillions of dollars and decades, if not centuries, if not millennia of time, and thousands, if not hundreds of thousands of scientists employed in the task to put these scientific tables together. Larson was able to more or less recreate them by himself with no money. So that, I think, gives you some idea of the power of the reciprocal system. Now, the reciprocal system is also called by Larson the universe of motion. Larson was not the first person to propose motion as the fundamental component of the universe, but he was the first person to actually make it work really by the way he defined motion. And this is really two ways of defining motion. One is that first he had to define motion as really what he calls scalar motion. And scalar motion is more or less a more flexible, non-localized, generalized motion. A motion that has a magnitude, but it has no specific direction. Which you can envision using a balloon that you put dots on. You blow up the balloon, all of the dots will be moving away from each other. So they are not moving in any specific direction. Every dot is moving in every direction, more or less. And even the spaces between the dots, the locations between the dots, are also all moving away from each other. If you suck in and contract the balloon, then all of the dots will be moving toward each other. So the only direction that scalar motion really has is out or in, one of the two. And it appears to have a direction if you arbitrarily decide to take one of the dots and assign it as the reference point. To basically say this dot we will arbitrarily say is motionless. And by doing that, then you can start determining directions. And so the outward motion of the balloon is what Larson calls the progression. And the inward movement is analogous to gravitation. And it appears as if there are gravitational fields there where you assign a reference point, and then all of the dots appear to be moving toward the one dot that you've assigned as motionless. So the gravitational field is not real. It is only the result of assigning a reference point where there is no natural reference point in that motion. It only comes through arbitrary assignment. So when Larson is talking about the force of gravity or the force, he really is he's really meaning an as-if force is what he calls it, an as-if force. It behaves exactly as if it were a force, but it isn't. It is just the movement of all of the dots toward all of the other dots. Okay, the other thing that Larson does in his universe of motion is that he defines it more specifically than some of his predecessors. So he defines motion as the relationship between space and time. And what that does is it sets up a generalized reciprocal relationship between space and time. Space and time are reciprocals of one another. Motion is basically a fraction with space or time as the numerator and time or space as the denominator. But also in Larson's postulates, he specifies that time, space, and motion all come with 3 dimensions. And so you have what Larson calls coordinate space and coordinate time. Coordinate space, we're accustomed to that idea. 3 dimensions of time, Euclidean geometry, x, y, z coordinates, and in a still frame. So it appears as if there is 3 dimensions, and that we're kind of moving through those dimensions as we move. But if we're still, those dimensions are still. This is an abstraction. This is like assigning a reference point. You have to assign a reference point to get that. But you really only assign a reference point in either time or space. So in this case, we're assigning the reference point to space, and time remains a scalar motion. Time is progressing or time is flowing, but in no specific direction, like on the surface of an expanding balloon. Time is always getting later and later and later, or further and further and further apart, but it's not moving in any specific direction. So we have a three-dimensional space and a progressing time. Now, what you also have to kind of understand about this three-dimensional space is that it takes 3 dimensions of space to describe one scalar dimension of motion. So in every 3-dimensional space, you really only have 1 dimension of scalar motion. So the other 2 dimensions of scalar motion can't really be expressed by any specific reference system. Now you have the same concept over on the other side. In a different sector of the universe, you would have such a thing as coordinate time and clock space. 3 dimensions of time in a still frame, and that is an abstraction. When you assign a temporal reference point, then you get this 3 dimensions of time in a still frame, and you get clock space. Space is always getting farther and farther and farther apart in a scalar manner, in no particular direction, like on the surface of an expanding balloon. So you can really have either one of those reference systems, the spatial reference system, clock time and coordinate space, or you can have the opposite or the inverse or the reciprocal as coordinate space, coordinate time and clock space. 3 dimensions of time and progressing space. And so those would be what you would call the spatial reference system and the temporal reference system. And they fit into different, and again, each one of those only occupies 1 scalar dimension of motion. And then you have another aspect of Larson's postulates called the discrete unit postulate. Space, time, and motion come only in discrete units. You have to have a full unit of space before you have space. You have to have a full unit of time before you have time. And if you have 1 unit of space in 1 unit of time, first you have to recognize space over time is what we call speed. The bike is going 10 miles per hour, 10 miles of space in 1 hour of time. Space over time. All motion is a relationship between space or time, a fraction with space or time as the numerator, time or space as the denominator. And they can be in multiple dimensions. In this case, in speed, they're both in 1 dimension, space over time. Now, if you change it to acceleration, and you say, I dropped the rock out the window and it fell at 9.8 meters per second, then you have space over time to the second power. That is acceleration, space over time squared. And also, you can see the reciprocal relationship in speed. If you decide to double the speed, you can say now the bike is moving 20 miles per hour. But equivalently, you could also say now the bike is moving 10 miles per half hour. You can either double the space or you can halve the time. That shows the reciprocal relationship between space and time in speed. Now, if you have 1 unit of space in 1 unit of time, which are both the minimum that you can have because of the discrete unit postulate, you have to have 1 unit to have anything. Kind of just like if you go out on the tree, you can't just say, go pick me half an orange. you either have a whole orange or you don't have an orange at all. Now, you can cut it into pieces eventually, but right off the tree, they don't come in fractions. So 1 unit of space and 1 unit of time is what Larson calls unit speed. And that's the progression of space and the progression of time. Every unit of time, there is a progression of space. And 1 unit of space and 1 unit of time is also known as the speed of light. So in Larson's universe, another thing that you have to be able to recognize is that in an empty universe, a universe that has nothing in it, you still have motion outward at the speed of light in all directions, a scalar progression in all directions in 3 dimensions. That is the empty universe. That is what Larson calls the 0 point, or the null point, the neutral point, or I could call it the origin, the ether. Larson also calls it the progression of the natural reference system. This, you have to be able to accept the fact that motion exists before anything exists. And in fact, the thing that eventually does exist is made out of motion. That's another kind of conceptual hurdle that you have to get with, is that you have to get with the idea that we don't... for thousands of years, we've thought of the universe as this drama that occurs where we move through our, daily activities on a stage of space and kind of unfolding through time. That space and time are the setting or the container of the universe. But in Larson's system, space and time are the contents of the universe. So basically, this speed of light is what Larson calls the progression of the natural reference system. This is always there, omnipresent, ubiquitous, eternal, and it is the stuff that the universe is made out of. By kind of like rolling back the progression, that is where you get, you can create atoms and matter in general. So you take that outward progression and you figure out a way to reverse it. And really the first step is the photon. And then after that, you get particles. If you roll it back once, you get photons. You roll it back again, you get electrons. You roll it back again, then you get particles with mass, and then you roll it back again, and eventually you get atoms. And so an atom is really a 3-number combination. It has to be rolled back in 3 dimensions. The photon doesn't really count. So the photon is a simple harmonic motion, a wave-like motion. There's dispute in the reciprocal system between Larson and some of his followers about how that photon was created, whether it was a birotation or whether it was a vibration combined with a translation. Either way, it's made out of motion. There are different forms of motion. And so, but getting back to this progression. So the progression divides the universe in half, basically. Half of the universe is moving faster than the speed of light. Half is moving slower. The half that's moving faster is called the cosmic sector. And the half that's moving slower is the material sector. The cosmic sector is basically unknown to science. The material sector is what we're comfortable with. In the material sector, we have coordinate space and clock time. In the cosmic sector, we have clock time, we have clock space and coordinate time. And so the rules invert when you cross that speed of light boundary. But within each one of those sectors is a subregion where the discrete unit postulate is also germane, that the rules also invert. So this is the unit space boundary and the unit time boundary. Within the material sector, there is a unit space boundary. When particles and atoms, molecules interact in less than 1 unit of space, which is approximately 1/500,000th of an inch 4.56 times 10 to the minus 8 meters, then it occurs in less than 1 unit of space. But if you don't have a full unit of space, you don't have space. If you don't have space, you only have time, because space and time are the contents of the universe. And so it's got to be one or the other or both. And so these occurrences happen in time. Larson calls that the time region. And so this is the region of atoms and molecules and so on. And when things happen, when you cross that boundary, the rules reverse again. And instead of seeing the progression moving outward and gravitation moving inward, you have gravitation now moving outward and the progression moving inward. The same is true in the cosmic sector, except with the roles of space and time reversed. So within 1 unit of time, you only have space. So Larson calls this the space region, and this is the region of cosmic atoms, cosmic molecules, which we know of as mesons or antiparticles. Now, in Larson's book on chemistry, he takes these atoms and he comes up with their various formulas for their various properties. Here we're talking about compressibility. He just derived this formula. Compressibility is the compression of a solid, in this chapter, compression of a solid to the point, and measuring, how sensitive various atoms and molecules are to compressibility. But in order to understand compressibility, you have to also include this progression, because the progression is inward in the time region, and gravitation is outward. So he has what you call the internal progression, or maybe the intrinsic progression, or the intrinsic pressure that is always there. Okay, so that's the first pressure, and then there is an external pressure that adds to that. So the main, so the formula he ends up getting is basically the fraction volume over the initial volume equals the square root of the initial pressure over the square root of the initial pressure plus the external pressure. That is the formula that he finally arrived at here. And another thing here that's important is that pressure has to be taken to the 1/2 power, or the square root, because in the time region, you might be asking, well, if it's only in time, then how can the progression be moving inward in space? Well, that is a very good question, because there is no space. There is only time. But we are anchored to a spatial reference system, so we only see time. We only see space. We do not see time. And so what we do naturally is the actual occurrence happens in time, but we see it in what he calls equivalent space. We see the inverse of it in equivalent space, because space and time are reciprocals of one another. But in equivalent space, we see it is a second power function. So what we see is the second power of it, not the first power. So that is something that occurs in the time region, that occurs in every aspect of the time region. The equivalent space is a second power relation. Okay, we'll try to read. Sorry, that was a little longer explanation, but we can still read a little bit here and pick up some more clues about compressibility. So we just talked about the equation, the volume over the new volume over the initial volume equals the square root of the initial pressure over the square root of the initial pressure plus the square root of the initial pressure over the initial pressure plus the new pressure the quantity to the 1/2 power, square root of the sum of those things. As this equation brings out, the internal pressure, P sub 0, is the key factor in the compression of solids, inasmuch as this pressure is a result of the progression of the natural reference system, which in the time region is carrying the atoms inward in opposition to their rotational forces or gravitation. The inward force acts only on 2 dimensions, an area, and the magnitude of the pressure therefore depends on the orientation of the atom with respect to the line of the progression. Now, when Larson uses the term orientation, he basically means it has to direct itself. It has to, where we're talking about a scalar motion, in order to establish any type of direction, you have to orient yourself. And if you have 3 dimensions, you're orienting it in 2 dimensions because you only have 2 dimensions that the progression is sensitive to or whatever. Okay, so it depends on the orientation of the atom with respect to the line of the progression, as indicated in connection with the derivation of the interregional ratio. Here's another complication that he's building in. Again, though, it's worth it to learn this stuff because, not only does it apply to chemistry, but it applies to astronomy, it applies to physics, it applies to every subject. So that's what's so great about the reciprocal system, is that it might seem complicated to learn it, but it's so much simpler than legacy science, because once you learn the principles, you can apply to every subject. If you're studying science, you have to learn a whole new discipline, whether you're studying biology or geology or physics or chemistry or astronomy. All these different subjects have a different discipline, and you have to learn a different nomenclature and different principles. But with the reciprocal system, you learn one set of principles, and you can apply it to everything, including economics and other so-called social sciences, which are now really going to be social physics under the reciprocal system. Okay, so anyway, as indicated in connection with the derivation of the interregional ratio, there are 156.44 positions of a displacement unit in the time region, of which a fraction AZ represents the area subjected to pressure, A and Z being the effective displacements in the active dimensions. You could probably unpack that sentence for an hour and still not understand it. But basically, the interregional ratio is the ratio between what is actually going on and what you actually see going on. It's what's lost in the translation when you're peering across a boundary, whether it's the unit space boundary, in this case, could be the unit speed boundary or the unit time boundary. They have different interregional ratios, but and there are a few depending on whether you're dealing with subatomic particles or whether you're dealing with atoms. They're also different, or whether you're dealing with photons. If you're dealing with photons, the interregional ratio is 128. If you're dealing with subatomic particles, then you're talking about 128 times 10 over 9. If you're dealing with atoms, then you're talking about 128 times 11 over 9. Because subatomic particles have 1 photon and atoms have 2 photons. And each photon adds another 9th because there are originally 9 possible positions of the photon. So anyway, we're talking about atoms here, so he gets 156.44. That's actually 128 times 11 over 9. And there are 156.44 possible positions of a displacement unit in the time region, of which a fraction AZ represents the area subjected to pressure, A and Z being the effective displacements in the active dimensions. Okay, there's only two dimensions active, and he assigns these two numbers that are the effective displacements. So not quite sure what he means, but I think if we go on, we can figure this out. The letter symbols A, B, and C are used as indicated in Chapter 10, Volume 1, which is called Nothing But Motion. That was his book on physics. We went over that like 6 months ago. The displacement Z is either the electric displacement C or the magnetic displacement B, depending on the orientation of the atom. Okay, those displacements are the part of the three-number combination of atoms, as I mentioned before. Each atom, instead of a one number on a periodic table, you know, like hydrogen is 1 and helium is 2, oxygen is 8. In Larson's system, each atom has a three-number configuration. The first number is a two-dimensional rotation. Second number is an alternate or secondary two-dimensional rotation. And the third, he calls those magnetic, okay, two-dimensional magnetic. And then the third number is a one-dimensional rotation opposite to those first two, which he calls an electrical rotation. And that third number, the C number, is optional. In the inert gases or the noble gases, that number is 0. And that third number can also be positive or negative, whereas the first two numbers are always positive. Okay, so sorry that we're not really covering too much ground here, but I'm hoping that I'm at least laying some of the background for you for future reference. Again, there's a lot to explain, and it seems utterly complicated, but you know, once you get it, then you won't be wasting your time, because you can apply it to so many other subjects that you come across in the reciprocal system as well. Okay, so the displacement Z is either the electric displacement C or the second magnetic displacement, depending on the orientation of the atom. So of these three number groups, you basically have the first number and then either the second or the third number as the two numbers that are relevant to the pressure, AZ. Okay, we're going to stop there, and we'll start up again tomorrow, try to make more ground, but